5 points.
Hi, welcome to the Institute for Astronomy. I'm Joe Ritter. Our usual person who introduces speakers is away getting mirror coded. I'm a physicist and work here, and we build instrumentation, and you've got several of you who've been here before. I see a few new people, so welcome. We do this every month. Often the topics are interesting technical topics, but we are also interested in promoting education. We have a number of educational outreaches programs here. And we also work with MCC, which is now, is it UH Maui?
I'm still confused.
Okay, well, we're working with them to develop some of their first 4-year science programs there. And so tonight, rather than talking about our educational things, we have one of our educational partners, Akamai, who teaches physics, astronomy, etc., and is renowned for being a great teacher down there and has been down there many years. And in fact, the positive comments I hear about classes down there, often I hear about from students who go, yeah, I took John's class in astronomy and it was great, I want to be an astronomer now, and things like that. So we're very lucky to have John Pye here tonight, and thank you, John.
Thank you, and here's the Thank you. So glad to have all of you here. Welcome to the IFA's winter series lectures. It actually, the talk is about different kinds of astronomy research and internship opportunities going on at now UH Maui College. And this, I'm only looking at a small subset of many things that are going on down there. So I'm going to focus mostly on what I've been beginning to get involved with. You may wonder what scuba divers have to do with astronomy on that slide. But it does actually play into this whole thing. This is actually me in the middle doing checkout dives for a couple of UH scientific divers. We were at 130 feet, so that's what those things are. But this is really what got me kind of involved in experiential education. And this is the last thing on ocean science, so don't worry. But I've been at Maui Community College, or UH Maui College, since 1982, so I've been there a long time. And I first got involved in experiential education through our Marine Option program when I coordinated this. And what was really interesting about this and what I really liked was we were taking students and giving them some really hands-on kinds of experiences. We were doing work at the individual campuses in the UH system, and then we would gather all the students together either on Coconut Island at the Hawaii Institute of Marine Biology, or it eventually moved to UH Hilo. And what we did was a 2-week intensive classroom experience and then a 6-day field school and then another 3 days back in the classroom. And what students were learning to do was coral reef surveys of various types. They were learning how to use different tools for coral reef studies. They were learning how to work in teams. They were coming back and putting data together, analyzing it, and giving presentations to their peers. And it was such a positive experience. I was involved in this for about 15 years. And kind of the offshoot of this was that students would then get hired by various agencies. I was a co-PI on a couple of NOAA grants where we were doing coral reef assessment and monitoring. And the students who had gained these skills were then being hired and paid to go out and do these field surveys with these agencies. So it was a really great thing, and it came full circle. And I just thought it was a really great experience. And so I was involved with that for a long time. In the late 1980s and early 1990s, I got involved a little bit with some people who were with Boeing. And at that time, they built a small prototype telescope out at the old RME site, Relay Mirror Experiment site above the Research and Technology Park. And they were doing mostly satellite studies, tracking satellites. But in the process of doing that, they were starting to find all kinds of asteroids. And this is back in the days before this really just took off, like everybody was finding asteroids. And a couple of people that I knew were involved in that and asked if we would be interested in bringing some students out and getting involved in working with them to kind of start monitoring and tracking and searching for asteroids. And so through a program that I had just gotten involved with, we started taking students out there. They had to have security clearances to work out there, so there were some issues involved with that, and then after 9/11, things kind of fizzled out for us, and that went away. But in the interim, we had students getting published in some of the little minor planet circuitors and things with some of the asteroids that we were discovering, and it was a real exciting time and kind of really got me into the idea of looking at astronomy hands-on experiences. And it related a lot to what I've been doing in the marine sciences for a number of years. So, but that kind of went away, but a little bit after that went away, the Fox telescope showed up. And a couple months ago, if you were here, you may have seen the talk that Wayne Rosing gave, and the Fox telescope has now kind of evolved into the Los Cumbres Observatory Global Telescope Network. Lots of things going on, not only pretty pictures, but they're doing science, and we're getting some students involved in some of those projects as well. We have an agreement that, so the people in the United Kingdom have time on the telescope. We in Hawaii have some time on the telescope. Usually at only very fixed times, so it's good for some things, but it's not good for other activities where we need more time for monitoring. So I've been sort of looking for a while at other ways we can get students onto telescopes and doing different kinds of projects. A couple of years ago, I was at a conference and a meeting with people who are actually involved in undergraduate education and research. We were talking about different projects we could get students involved with, doing science collaborations with professionals and amateurs, using different kinds of instrumentation, and I met the owner at that conference of what was then, brought my own laser pointer, let's see, was the Sierra Stars Observatory. There was one observatory, it was owned by him, it was a private facility, and people paid money to use it, and you could get the data from that. It has since evolved into a second a telescope that's now part of what's called the Sierra Stars Observatory Network, and a third one is coming out soon in Australia. They have some nice telescopes and cameras and instruments and things, and it costs money to use it, but as a result of that meeting, I was given a block of time to utilize the telescope to test it out, because I was talking about some of the kinds of projects I was interested in doing with students here at the college. So I went and I had several things I was interested in, and just to give you a little clue of what I did, initially, one of my areas of interest, I'm interested in asteroids and variable stars and things related to exoplanets, and especially photometry and that type of thing. So I thought I would use this telescope to, I had a favorable opposition for the asteroid 216 Cleopatra. And I was given enough time where I could actually monitor it for a little over 5.5 hours, and I'll show you why I chose that time frame in just a minute. But this is a sample image. This was a 20-second exposure. The telescope is a 0.6 meters, so it's a nice telescope. And this was through a red filter, but this was one of more than 80 images that I had taken over a course of about 5.5 hours. And the reason I show you this particular picture is because I wanted to show you how the field of view of this telescope, which is a little over 20 arc minutes by 20 arc minutes, it's a little less than the size of the full moon. So you're looking at a fairly small piece of the sky. But the Fox telescope, this is the field of view of the Fox telescope by comparison. Now there's a lot of things the Fox telescope is really good for. It's a 2-meter telescope. It can peer into that area and probably see things this telescope can. It can collect a lot of light. But you can also see that what you're looking at is a much, much tinier piece of the sky. There's reasons that that's an advantage, and there's reasons that that's a disadvantage. If you're trying to monitor things moving through the sky, if you have a little tiny field of view, you might totally miss what you're looking for. And so Pan-STARRS is kind of that way. It wants to see a big piece of the sky because you're looking for things that are changing or moving. Okay, so what can we do with these kinds of images? Well, there's a couple things that I just want to mention initially. We can find asteroids, possibly, if we're lucky. We can also measure precise positions and movements of these objects through the sky, because we can access databases or star catalogs that give us very precise positions of stars in the field of view, and then we can measure the position of the asteroid or other objects relative to those and be able to track its accurate movement through the sky. Just looking at those 4 pictures, that's 4 out of about the 80. Can anybody see anything different in there?
Lower right one, third of the way up to the bottom on the left.
Oh, I
There's
see.
a star that is not in the other ones.
Clear.
Well, that may not be from something moving in, it may just be from the telescope not tracking.
Looking at the central star, there's a star, something that looks like it's moving at about the 1 o'clock position.
Okay, so here's the thing. it's pretty hard sometimes, without a trained eye, just to look at pictures and say, is anything moving in that? Is anything changing in those pictures? And it's not, because they all just look like dots, right? So, yeah. So here's what I'm going to show you. What you do is you kind of take these images and you stack them together. So this is a sequence of images taken over that 5.5 hours. It's about 88 images roughly. You stack them together, and what that basically means is you kind of align them all up, and you take and match all the star patterns in all these different pictures, and then you animate it. Okay? So let's go ahead and animate it, so you can kind of see what's going on here. Now in that case, everybody can find it, right? So that's pretty good. So what this shows you is that this object is definitely moving through the field of view, and if we could measure those accurate positions over that course of time, we could tell not only where it is in the sky, but we could tell how fast it's moving. You can use these things to predict the kinds of orbits it would have, all kinds of things. So that's a real easy one to find, and one of the things that makes this a nice picture is that everybody can spot that.
There's two dots on the left too that show.
Oh yeah, okay. So there's lots of other little junk in there too. And this is something I actually have my students do in my lab class, not only with this image, but with a bunch of images, is when when they get really focused and say, okay, I'm looking for something that's moving, everything's moving. And all these little dots and noise and things. And so we talk about how do you distinguish noise, for example, from something that's real. And you look for certain patterns, and you look for different kinds of things. And so I'll tell you that everything else in the image is not an actual celestial object. It's noise from the camera. Most of these are calibrated images, which means they're fairly clean, but there's still random noise that you can't clean out of those things. Now this next one I want to show you, it looks really great on my computer screen because I can see them, but I realize that the resolution on this projector isn't that good. But what I wanted to show you, this is a different sequence of images, 5 images taken over the course of approximately 10 minutes. And in this thing, you're maybe looking now, again, you can see those little bits of noise and stuff in there. There's actually 2 asteroids in this picture. And because it's pretty hard to see, I don't know from where you're sitting if you could even see it unless you're really right up here, but there's one right there. And it probably doesn't show from too far back. But there's actually 2. And I put this up here for a couple reasons. One is not every asteroid is as bright as that last one we looked at. And so it's not always very obvious which one, what are real and what isn't real. So this is part of finding these things or following up on tracking them and that type of thing. Okay, so that picture is kind of a disaster because you guys can't see what's up there. If you're interested, I'll show you after I'm done. Okay, back to this one. So we all know we can find the asteroid. So that one of the things I wanted to do, of course, was find the asteroid. But the other thing that I was interested in doing was something called photometry, which is measuring the brightness of this or how it might change over time. So we can also measure brightness variations. Now, when you just look at it, it pretty much doesn't look like it's doing anything. But if you actually have a detector that can is sensitive enough, and then you have software that you can use to actually measure precise levels of brightness, you can actually see that this thing is changing over time. And in the case of this asteroid, it turns out to have to do with the fact that it's spinning, it's rotating, and presenting different sides to us. So let me show you a very simple way to try to imagine this. Okay. So we could pretend that we have like this cube that's spinning around. And let's just pretend that sunlight or something is hitting this face and it's reflecting it back to us. And so we're detecting a certain brightness reflection from the sun. So because that's a big face, that means that if we were to actually plot how this brightness changes over time, we might see that when this face is illuminated, it's pretty bright. Now you imagine that this turns like a quarter of a turn, and now this little face is pointing toward this. And it's not going to reflect as much light back to us, right? So we would see the light drop in intensity. Now the next face comes around, it gets brighter again. The next face comes around again, it gets dimmer again. Does everybody kind of see that? Now, this is a very idealized case because you know, we're assuming everything's reflecting perfectly and all that. But you can imagine it could be a lot more complicated with a real asteroid, for example, whose different surfaces, you know, they're not nice and smooth and they're rotating in funny ways. So you could get a lot of different kinds of curves, but people are pretty good at interpreting those curves to give you some kind of indication. So this was the other thing I was interested in doing with this particular object. Not only finding it, but I wanted to measure its brightness variations over time. So you can see that if it's rotating, you should get some kind of repeating pattern. Okay. So I did the measurements, and here's what I found. And this is called a light curve. So you can see that it's going from you know, bright to dim, and bright. And the way we do this is we measure the brightness of the asteroid, and then we compare its brightness to other stars in the field. And usually we compare it to a couple of them, so we know that the thing we're comparing it to is not changing too. You don't want to do that. And so this sort of shows the comparison stars that we use, so you can see that they're fairly stable. And then this shows the intensity variation of the asteroid during the same time. And you can actually, by measuring the time that you do that, get an indication of how long it takes to rotate. And it turns out it's a little over 5 hours, which is why I chose that 5.5 hour block of time. So you can do some cool things with this. You can, you know, not only track asteroids, but you can measure the rotation rates. People can do things using other kinds of instruments to learn a little more about their composition and all kinds of stuff. So it's really cool. And this was what I was using to test with this particular telescope, because I wanted to see if I could get students to do the same thing. Okay. Now I think I mentioned that telescope is not cheap. And so I've had to write a few proposals to get some money into a fund that I could use to allow students to get time on that telescope. The Fox telescope I mentioned is free for educational use, but we have very limited time on that telescope. So I'm looking for, like, how many possible things can I pull in here to give our students the most possible chances to actually get hands-on experience with this. Last year I gave a talk at a joint meeting between the American Association of Variable Star Observers and the Society for Astronomical Sciences, and I met some people who got me to write a proposal to this foundation, which is a non-profit foundation who's dedicated to making instruments available to educational institutions that have projects that they're interested in working on. And you write a proposal and you go through all of this. And this is only a few of the types of telescopes that they have, but they have quite a few different telescopes available. There's probably another 3 or so I couldn't fit on the slide. These are in New Mexico at a fairly nice elevation, nice dark skies. These telescopes are all robotic or remote, so remotely operated. So my students can sit here at home or, you know, at school and control these telescopes via the internet. And they can collect data and download their images and then do some projects that way. So we've been starting to use this. This foundation has 2 sites that they use, one in New Mexico, and the second site is in Australia. So what's really cool is we have kind of a global network in a way. And there's lots of reasons, and I'll mention a couple of them in a little bit, why that's an advantage, to have telescopes in more than one location. And this is part of the philosophy of the Los Cumbres Observatory Global Telescope Network, is there's a lot of good reasons why you want things all over the place. Okay, so this is kind of what we're doing recently. Now to bring it back home just a little bit. This is up at Haleakala. I can't even remember how old this picture is, but it's around. But this is one some of you may not have seen. Some of you probably have. This is the original building up in Haleakala, the old Baker Nunn, which is still there. This was in the 1950s when it was first put up there for satellite tracking, and it was functional for a long time. I just try to imagine what it must have been like up there during that time. It must have been amazing. This one little tiny building. Here's where the Fox telescope is. Here's where Baker Nunn currently resides. And then there's all the other facilities up there. And this comes back to also an affiliation with an incredible group of people on the island, the Haleakala Amateur Astronomers. This is Rob Rutkowski, the guru and in charge, who's made everything pretty much happen. And the Institute for Astronomy has been incredibly supportive and allowed us access to the old Baker Nunn site. And we've been doing a lot of things up there, trying to transform as much as we're able to do into something that we can utilize to allow students and do public outreach and education up there. And it's starting to work, and the HAA is a great group of people. They're really excited about what they do, and they share everything with people who come up there. And I've taken several classes, mostly my lab classes, up for field trips. And you can see it was a little crowded and a little tight, and the IFA has given us a lot of support and encouragement to kind of, you know, bring things together. And so it's changed quite a bit. This became that, and became that. And we now have a very nice facility for students to come up and work on the web and run the Falks telescope. We also have a small telescope, well, a 14-inch telescope that was donated to the college. It's now up at the summit, and we're working with some students at the college to actually automate this thing eventually, where we can do some work with students up there. So what we're trying to do is kind of supplement this whole network of tools that are now available that really were only in the realm of professional astronomy not that long ago. These things are now available. There's amateur astronomers that have their own observatories all over the mainland that rival some professional observatories. I mean, it's amazing what's out there and what people are doing. And the collaborations that are starting to occur between amateurs and professionals is really taking off. And amateurs are contributing good data. They're getting published in these professional peer-reviewed journals, you know, along with the professionals who are actually doing the projects. And this is a great place to get students involved. And this is part of really what my interest is as we go along. So, besides the programs I've talked about that I've been involved with, there's programs that have also taken off at the college through the support of the Center for Adaptive Optics, which is funded through the National Science Foundation, and one of their big benefits has been the Akamai Internship program, and they've partnered with many people around the island and companies for students that are interested in getting into high-tech careers, engineering or other technical support careers. And so the Akamai program has a short course that they offer every summer, and then paid internships over the summer where students actually go out to these companies and work on various types of projects. This is just a very, very small listing of the things that are going on. But the idea is that there's really starting to become a connection in this community between the high-tech companies and other people that are supporting astronomy and students that are interested in going into these fields. So it's been a great partnership, and a lot of what they're doing in the Akamai program was very similar to things that I was doing, as I mentioned, in the mid-'80s and early '90s. The philosophy is the same. You get students involved by giving them hands-on real-world experience. You get mentors that are willing to work with them. You get students actually excited about doing something, and you give them opportunities to go. And so the Akamai program went from there. Most of those are not my students. They're in the ESET program, the Electronics and Computer Engineering Technology program. I get a few of them that come through, and they've also linked into this program, which I'm the Associate Director of the NASA Space Grant Program on our campus. And so I manage that grant and also get support to provide students paid internships for working on projects. So a few of those students from ESET and Akamai have continued past the Akamai internship into the academic year, and we've been able to support some of their things. But since these are mostly not my students, I've been looking at how can I do this for students that are in astronomy courses that have an interest in astronomy. So this is sort of where I've gone with this in the past couple of years, maybe 3 years or so, since I developed this course, this new lab course at the college. We never had a lab course in astronomy, just a lecture course, and it sort of to me almost felt like a dead end in a way, and students always wanted to, they would say, is there more we can do? Is there something else we can do? And we really never had anything, but through a period of time I was able to develop this course, and because it was on our campus, and although it sort of fits into the system-wide astronomy lab kind of philosophy, I turned it into what I wanted to do for the students, because I had my own sort of reasons for doing that. Not only to give them what I thought was more real-world, hands-on kind of experience, but I wanted them to come out of this lab course so if students were interested, I could take them right into doing some of these research or internship projects without having to start from scratch. They would already have some experience. So we run through a lot of different things. They learn how to do some basic image analysis and calibration and processing, because they love images anyway, so you start teaching them about all the things you can do with them, and they get excited about that. We work on astrometry and photometry projects, very rudimentary spectroscopy. They conduct observations, both real world using telescopes, it might be the Falks, it might be other things. We also have software where they do simulated observations and collect data. Then they learn how to kind of analyze that data and present it, and the results of that, and they learn how to use lots of different software and things. So by the time they're done with this course, they get quite a bit, which some people have said, I think you're making them do too much for freshmen and sophomores. They've all pretty much risen to the occasion, and they're into it. So it's like, let's go for it. My other motivation is when the students get out of the lab, those that are interested, I've got things for them to do. I've got money to support internships. I've worked with people on science collaborations, and J.D. Armstrong and I are now talking about a mentoring program between students at the college who have gone through some of this and students in the high schools that are interested in getting involved in different kinds of astronomy research. So we're just now starting to talk about how we can bridge that and get people involved. So there's a lot going on. Unfortunately, when I developed the course, there was no lab manual out there that existed on the market. So I wrote my own, which it's like it never ends. You know, it's like, oh God, now I got to do this, and now I got to do that. But it's okay. It's taken me a couple years, and it's pretty lengthy and all that. But it's got a lot of stuff in it, and it does what I would like them to learn from this, and it leads them through everything, and it's got all the main topics that I'm kind of interested in covering. Now, just to follow up, I'd like to talk about something that we did about a year ago. One of my first students that got out of the lab course, her name is Alder. She's now finishing up her sophomore year at the college and is planning to transfer. She's interested in majoring in physics or astronomy. But she finished the lab course, and about the time she finished the lab course, I got an email from someone who was interested in working on a variable star project. There was an eclipse of a star that was occurring in 2009 that only happens once every 5.5 years. And it turns out that they were organizing an international observing campaign, and they were looking for people to get involved with this. So I didn't realize how much it was going to take when we started this, but I said, okay, we'll do it. Lauren said, I'd like to do that. So we got her involved. This is the title slide, actually, from the talk I gave at this joint meeting last year. But I want to talk just a little bit about what occurred with this and kind of where I hope some of this goes. So how we got involved? Well, in December of 2008, an email request went out. I'm not going to read all of this to you, but basically it was describing what the project was. They were looking for people to be a part of this project and to take images from this robotic telescope in Arizona, download the images, go through a bunch of analysis and photometry, and then get this stuff reduced, and eventually turn it into light curves during this eclipse. And there was a number of reasons why they wanted to do all this. So anyway, and it wasn't really what I would call a difficult project, but it was very meticulous and things had to be done right. And it wasn't sort of like, okay, Lauren, just go for it and see how it goes. People were depending on the results. So this puts a little pressure on you at that point. So for about a month before the real eclipse was taking place, I was collecting data from the telescope I was doing my own photometry just to get results, and then I would give Lauren the same images and say, now you do it. And eventually we got to a point where her technique was very good. Our results agreed within a fraction of a percent, and I kind of went, okay, you're ready. And she pretty much was on her own for about 2 months, working and analyzing the data. Now, just a little, so anyway, I guess I didn't see this before. But, you know, a lot of stars change, and they change for various reasons. Some of them pulsate like this, and that's one type of variable star. Other stars might change in brightness because they're being eclipsed by another star. And these are all different. Stars that are like this, the right kind of pulsating stars, you can actually measure how their brightness changes over time, and you can use that as a distance indicator to measure how far away something is, a galaxy, for example. There's a lot of cool things you can do with it. And eclipsing stars, eclipsing variable stars might be 2 stars going around each other. In some cases, it might be something like an exoplanet passing in front of a star. Now, I don't know how easy this will be for you guys to see, but this is the sun, and if you look really, really, really close, can you guys see that?
Yeah.
That's Mercury transiting the sun. Okay, so you can see how small Mercury is by comparison. Now, this might be the kind of thing you might observe from the Earth, looking at a star. If a planet happens to be moving across the face of that star far away, now it's hard to imagine that something like that could make the light of the sun change by very much, right? I mean, it's like, how am I ever going to figure that out? It's like if a mosquito flies in front of a spotlight or something. But instruments can do that. Certain instruments are capable of doing that. And so what we actually see is maybe something like this little animation shows. When the planet passes in front of the star, the light drops in intensity, and when it passes on the other side, it goes back up again. When that planet comes around again, we see the same thing. And so you can watch that over time, and you can start figuring out things like, how long does it take that planet to orbit that star? Which tells you how far away it is. And you can figure out things like mass and size. And there's a lot of different things you can do with this. But the idea is there's lots of things that change. Now, this particular variable star wasn't an exoplanet system. There were just 2 stars. And what we actually have, I'm not going to get real detailed on this, but I just want to show you how the history of this particular object kind of came to prominence. In 1947, astronomers, for the first time, noticed that it looked a little fainter than it had before. So people probably hadn't really been looking at it for very long, and all of a sudden one year they went, oh, that thing looks kind of dimmer. So fine, but that sort of prompts people to kind of keep watching it. Okay, what's going on? So they watched it and watched it and watched it, and in 1952 it became fainter again. And they went, wow, okay, something's happening. In 1958, same thing. So people started going, I think something's repeating itself here. And it was first suggested that it might actually be an eclipsing binary star. So then people started getting a fairly good idea of how frequently that was occurring. So they watched it again, and in these years, the eclipsing nature was confirmed. They got the detailed ephemeris published. It showed a period of about 5.6 years. So every 5.6 years, this system is eclipsing one another. Now, what was interesting about this was, remember how we talked about these little light curves, right? And you might think, well, if it's just eclipsing all the time, they should all look the same every single time. But in fact, they looked very different every single time. Something weird was going on, and the system wasn't very well understood. So as people were observing, the last eclipse that had occurred before this previous one in 2003 was very different. Some of them were deep eclipses, some weren't so deep, some had flatter bottoms, but they were really interested to see what was going to happen in 2009 and to try to understand more about the system. Now, there's a lot of words here, but the basic thing is they had done photometric studies, they'd done spectroscopic studies, they looked at the shapes of the light curves, and it turned out that what was proposed in 1999 and then again in 2003 was this could best be explained if the secondary, which was the thing doing the eclipsing, actually was a dark, opaque, relatively thick disk around another star. It wasn't just two stars, but that star had something else around it. And they did color filter observations, and they did lots and lots of stuff. So all these words can kind of be summarized in these two pictures. Here's what they kind of thought. This was the primary star, which was a very hot, rapidly rotating star. This was, in the middle, was they assumed was a secondary star with some kind of circumstellar disk of material around it. And what they noticed, though, in the 2003 eclipse was that something like 9 days, I forget the exact number, before and after the main eclipse, where the center actually passed in front of that star, there was these little bright, intense rises in the intensity of blue light. And you couldn't explain that if this is what the system looked like. It just didn't work. And other people were predicting the different shapes of the eclipses and things because this disk was probably precessing around, kind of like a gyroscope, and it was presenting different, sometimes it was flat and sometimes it was more tilted, and so that would change these particular types of curves. But these increases in intensity could only really be explained if that disk wasn't solid, but it had kind of a gap in it. Because then you can imagine as this thing moves in front of that blue star, the light starts to fall off, and then when this little blue light reaches that transparent gap, you get a little shot of blue light. And then everything disappears behind this one, and then you get another shot of blue light in that transparent gap. And so they thought, maybe this is what the system looked like. And they were trying to answer all these questions and trying to confirm the nature of the system and a bunch of other stuff. So this is what the international campaign was about. That's just a little brief background on that. How we then got involved was actually working with the Sonoyta Research Observatory in Arizona. It's a privately owned observatory, but the American Association of Variable Star Observers has 1/3 of the time on that telescope for various research projects. So we were able to get time on that telescope. And it was set up for a period of about 2 months. Every night that they did an imaging run, it took 8 images, 2 images through each of 4 different color filters. So that was the thing. And we were getting all these images every day almost. This was the reference chart that we had. So these 3 stars, remember when we talked about the asteroid thing, we talked about we have to have stars that compare the brightness to. So these were our 3 comparison stars whose magnitudes were known, and they were known not to be variable stars. And this little thing here was the star we were interested in. That was the variable star. Here's what the actual pictures look like that come off the telescope. Those 4 stars are the 4 that we saw. Stuff is kind of reversed and things. But anyway, these are the 3 comparison stars, and that's the variable star. So these are the images that would be calibrated, cleaned up of noise and other artifacts. And then Lauren would download these images from their server to our computer, and then she would begin the process of measuring the brightness of all these stars through each filter, 8 of these images a day. And the technique, and this is Lauren up here, working on the project in our Space Grant office. And the technique we use is something called Aperture Photometry. And what we do is you use software to kind of make this little aperture that the light comes through. And the software looks inside this aperture and it says, what's the intensity of light coming through to my detector? And it measures that. Now the only problem is when you put an aperture around a star, notice that you're also getting some background sky in there. And we want to and the sky gives off light. Maybe not a lot, but it gives off some. So we want to get rid of that so that all we're collecting is just the light from the star. So we define another aperture that just picks up background sky. And then the software automatically will read that intensity, subtract out the background, and give you an intensity reading for that star. So it's really cool. It does it all for you. So she was doing that. She had to go through the header, the image headers, and know which filters were used, what times, exposure times, everything. So she had to extract a lot of information from these images. And then she would take those intensity readings and record them in a lab book and then eventually enter them on a spreadsheet. So this is just a couple of days, but you can see this is quite a bit of stuff that she did. We would then take that data and enter it into a program that would convert normal day and time into something called Julian date or heliocentric Julian date, which is an easier way to kind of keep track of days. It would know the position of these objects in the sky, so it could measure what's called the air mass, which is the thickness of air that the stuff's coming through, so you can compensate for how colors are affected, and lots of other things. So it does a lot of work for us. And then it applies what are called transformation coefficients, kind of a scary sounding thing, but what it does is it takes into account that everybody's telescope and camera and filters are slightly different from everyone else's. And so we need to, what we're trying to ultimately do is turn this into a reading that everybody agrees on. So if I read how bright a star is from my little telescope here on Maui, and somebody reads how bright a star is from their little telescope in New Mexico, and it's the same star, we're not going to agree on what that number is because our instruments are all different. So we have to have a way to figure out how do we know what the real number is. And we have transformations and things we can go through to turn those into real magnitude numbers, real brightness numbers. So that's what we were doing with this software. And then finally the results would get entered here, and we would have real magnitudes in each of the filters for 1 day of observations. And we would go over and over and over for all these days, and then we compiled all the data from November 2008 until February 2009. These are average intensities, so these were the averages of 2 images, and did the statistical stuff and all that. And this is the compiled data. Now, you look at those numbers and you go, that doesn't tell me a whole lot. So the thing you do is you graph them and you make pictures. And that's what we did. So these are our light curves. And these are you can see we caught the eclipse perfectly. We were measuring different characteristics of the eclipse curves. These were the curves generated from all of our data in the different filters. So there was 4 filters, so these are our light curves. This is what we did with all of the transformations and everything. Lauren didn't do this because this is sort of beyond the scope of what we get into in the lab. But they learned how to do what's called differential photometry, which is a more simple way to do things, but you get essentially the same results. So, not to be outdone, she said, okay, that's fine, I want to do my own. Because in the lab, they learn how to make light curves. So here's hers. Now what you can see the difference is, these are just measuring differences in brightness and not absolute, real brightnesses, which is fine. Notice you get all the same characteristics on the curves. So these were her curves that she actually did on her own because she just wanted to do it. And you can see how her curve compares with the real curve. I mean, they're the same. They're just, the scales are slightly different. So she did really good work. And, we got her comparisons against all of them, and everything was great. Okay. We compiled all the results. You can measure things like how long did the eclipse last and all these kinds of things, and you can compile all this data. And all of this was sent off to the people coordinating this observing campaign who happened to be in Poland, but this was a fairly international collaboration. And we also did color filter readings. I won't get into the details of that, but anyway, we're doing color things for various interests they had. And then all the data, these are the people involved in this campaign. You can see it was fairly international. There's people in the US and Europe, all that. This was our data here. And it was kind of gratifying to see that ours weren't like here, 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 and here, and everybody else's was in one place. So we did a pretty good job. I want to point out one thing, though. Here was our light curve, and one thing you might see if you look carefully is this sort of bump right here. And you look at our light curve, and it's not there. And it's like, oh my God, did we screw it up or what? Well, it turns out that we didn't, but this occurred over a period of something like 6 days. And there was really bad weather at that observatory, and we couldn't get data. So isn't it kind of weird, though, that the days we happened to miss were the days where the real interesting stuff turned out to be happening? It happens. This is why people like to have lots of observatories all over the place, because that kind of thing occurs. And when you have a big international collaboration, or even a collaboration of just 2 or 3 people, you pick up things that somebody else might not, because they had bad weather, their camera went bad, something else happened. And you compile everything and put it together, and you get a complete, set of information. So, and it turned out this was a critical piece of information, because this gave them a clue. Not only did it confirm there was a gap in the disk, but later on it confirmed that there was more than one gap. And so here's some other data, so that all worked out. And then Lauren gave a talk on her work at every year the NASA Space Grant Program has a student symposium, usually at UH Manoa. So she went over, she put her presentation together, and she gave a talk to a group of people ranging from sophomores to seniors at Manoa on her work, and did a great job and got good reviews from that. So to me, this was kind of how it all came full circle. You learn how to do these things, you go out and do them, you put your stuff together, and she's learned a lot of skills that she's going to utilize in a lot of other areas. Whether you do astronomy or not, you learn a lot of skills that you can do in a lot of different areas of life. And so she did a great talk, and for this joint meeting, I'd written a paper. She got listed as a co-author for all of her work. So she was just finishing her freshman year. She did this research. She's listed as a co-author on a paper. Then the person in Poland who organized the international campaign, a month later, he wrote a paper that went to an international conference in Europe. She was listed as a co-author on that paper as well. That helped her, in fact, when she was applying for different schools as she was transferring. Not too many freshmen or sophomore may have their names on a paper somewhere. But this paper described, in fact, what they discovered with this last eclipse was that there was probably more than one gap, and they now speculate that it's probably because some kind of massive bodies are in there creating these gaps of material, and they think it might actually be a protoplanetary disk where planets may be forming. So the next campaign, they've already laid out what they want to do, both with spectroscopy and photometry. So hopefully I'll have students ready for that one, and they may start finding things that have to do with protoplanets, potentially. Okay, almost finished. Here's some of the current things I'm doing with this particular foundation. I have 3 students working with me this semester, and they're learning how to do remote observing. They're using these telescopes both in Australia and New Mexico, and they're learning a lot of stuff. One of the things they're learning how to do, first of all, is to choose a target that they want to look at. I'm interested in an asteroid or a variable star or a comet or, whatever. They choose their target of opportunity, and once you say, I want to observe that asteroid, then what? Well, you have to know where it's going to be, when it's going to be there. You have to, once you know all that, you still have to be able to somehow get the time on the telescope during that time you want it to be. So they're learning how to plan observations. They're also learning how to schedule observations, because this network of telescopes has a scheduler, so they can go many months in advance if they want. They can schedule times. It's heavily utilized. So there's times they've learned that they wanted to be on that telescope on that night, and it's already booked. So they're starting to learn how to look farther ahead sometimes to get blocks of time that they might want. So they're learning how to schedule. They're characterizing some of the different telescopes, because there's really not a lot of information on these, and they're compiling kind of user manual notebooks for future students that we'll have working on this. So they know things like, I want to image it something of this brightness, how long do I have to expose this, because these telescopes are all over the place, so there's not one set answer for that. They're learning also how to retrieve the data once it's stored on the servers for these things, so they can download it on their own computers and they can begin to work with it. So this was what we started doing this year with this network of telescopes. They're one of the things they've been working on a lot is asteroid astrometry. So to do that, because asteroids are always moving, you can't just go out on any given night and say, I'm just going to point the telescope there, because the next night it won't be there. So they have to actually go to something like the NASA JPL Horizons website or other places and figure out what the coordinates of that asteroid are for every hour or even minute, if it's a fast-moving asteroid, for a given day that they're going to be observing. And once they know where it is, then when they go onto the telescope, they know where to point it in order to find it. And they're learning, about various imaging requirements, how to submit the data. They're starting now to get to the point where they're looking at follow-up work that's been requested by the Minor Planets Center. So there's lots of different things out there. And in the future, we'll probably be doing more of these kinds of things as well. So they'll be doing more light curves with the rotation of asteroids, some variable stars. Looking for exoplanets is kind of like, well, it's not like on these we would necessarily discover a bunch of them, but we can certainly do follow-up work. And, Pan-STARRS is going to find tons of things, and they're probably, hopefully, someday going to say, here, we got lots of stuff. You have people who can sort through this data and help us find what's going on. Here we are. Okay, so I got some students that are interested in that, and we may do some other things too. So that's kind of what's been going on in this area. I'll end by showing you kind of where all this will hopefully be wrapped in the not too distant future. We are getting a new science building at the college. I've been working on this for the last 8 or 10 years, I guess. So that's pretty fast compared to most things in the UH system. But we got it fast-tracked, and we've been able to, and we desperately needed it. This is really going to be a great facility. It's all going to be photovoltaics on the roof, and it's going to be a LEED Gold certification is what we're shooting for, very energy efficient. The big thing is we're going to have dedicated labs for all the different programs. The bids have all come in now. We've gone out to bid, the bids are back, and now we're sorting through everything, all the sort of minutia of which bids, before we can award it. We're hoping to break ground not too long, and it'll probably be 18 months to 2 years when it's finished. And this is kind of what the floor plan will look like inside. Dedicated labs for all our programs from marine science to astronomy and optics and physics. We'll have a large lecture hall of 120, so we can also use it for community meetings and other kinds of things. We originally had in the design a community research lab, so we could bring people in from the professional community to set up experiments and do work with our students. This has kind of now evolved into something with adaptive optics and the ESET program, but that's okay. We can do lots of great things still. The other thing about this design is we're going to have a library and resource study center for students, and what never seems to happen on the campus is we're all spread out all over the place in weird different buildings and no connection with other science faculty or students very much in that sense. So one thing, I saw this design at another campus somewhere, and I wanted to incorporate that into this building, which is all of the faculty are all together and in a common place where students can come in and work and do other things, and we can interact a lot more. And it might actually be like, being real faculty, fine. So this is what I'm hoping for, and this is going to be a great addition to the campus and the community. There's some 4-year programs beginning to develop. Lots of stuff going on, so we're keeping pretty busy, and lots of opportunities, lots of interest by students. We've had lots of support from the community, and we're appreciative of all that. And I appreciate that you came, and I'm finished. So,
So, John, let me start this off with 2 questions. So when are they going to have the biology internships so they can fire up the cloning machines, get more teachers like you?
Oh, now.
Well, okay, so my first real question.
Okay.
You are going to have a telescope in the building, and on the building, right, I thought?
Well, let's see. It's not really shown here, but a little sort of history on what's happened with this. When we originally started designing this along about 8 to 10 years ago, there was a certain budget that we were told we would have to work with, something in the neighborhood of $39 million. So the original design was 2 stories. It had more classrooms, it had more labs and things. And about 2/3 into the design, we were told that, well, now it's going to be about $24 million. And although in this economy we're lucky to get anything, but this has been in the works for a long time. So we had to really scale back. We had to sort of, merge some labs together. We had to take it from 2 stories to 1 story. We had to do a lot of stuff.
Non-essentials like telescopes or...
Well, so what those now became is something called, I don't know, for lack of a better word, add-ons. And so there are add-ons to this building, which means they're not in the proposed design money kind of, this is the budget you have to build your building. And what became the add-ons was the lecture hall, which we all thought was a critical component of this. So that's an add-on. That's the #1 priority add-on. We have a small observatory, which is #2 priority. And we know we can't do the best astronomy in the world from Kahului, but that's really not the point of that little observatory. The point of that is to integrate it in with the lab and everything, to have some telescopes there that students can actually learn how to use and get hands-on experience, how the instrumentation all works together, so that when we do have them using other telescopes, they understand how to operate filters and which filters do this and how, slewing and getting target and all that. So it's going to be a lot of a kind of training, although we can get some information probably. And then there's some other things that are add-ons. So we didn't really know the status of that. But as the economy began to really tank, it turned out you get more for your money when people are out of work and contractors are bidding competitively for your building. We had I forget the number, 9 or 10 very competitive bids, although they ranged in amount by quite a bit. And we're sorting through those now, and everything has to be just right before we award it. But if we come out with a low enough bid, all these things will be included in the building. So I guess all I can say right now is they're in the design, but we don't know yet how it's going to work out in terms of what's going to be there. But if it is, there will be a little observatory and things over here that'll kind of integrate in with the building. So we're hoping that works. And then we think that'll be a great addition because that gets people a little more interested and excited because there it is right there on campus. And you can walk out there and you can have your courses and you can tie it into everything you're doing, even to the lecture classes. So I hope that answered that, and I hope I have better news to report. Yes?
What size and type of telescope did you use for this EEC, this photometry?
It was a 0.6 meter, I have it written down somewhere. It's been like over a year now, and I kind of forgot. Let's see. I knew my mind would go, and somebody was going to ask me something I couldn't answer. So there it is. Let's see. So yeah, it was a 50 centimeter Schmidt Cassegrain. It was mounted on a Paramount. Had all the array of filters and nice camera and all that. 1 1/4 arc seconds per pixel image scale, which isn't bad. It's good for photometry, not the best necessarily for real accurate astronomy.
Half a meter,
yeah. So it worked out pretty well. Yes.
And that star that you were just talking about, the CQ1, what distances are you talking about? How many
I don't remember. Sorry. Yeah, I probably should have had all that better together.
I don't. In the near universe, or is it?
Oh well, yeah, it's in our. I mean, certainly in our galaxy. Yeah. But I can't really even give you a good scale if we're talking like 50 light years or 300 light years or something like that. But there are limitations, certainly, especially with that size of a telescope, where as you get too far away, then you don't have enough sensitivity to really detect. And I should say that the change in brightness, the magnitude difference, was less than 1 magnitude, which means something like a factor of about two times the brightness. So that's not a big change, not something that typically, especially for a star that distant, that you would ever see with your eye. Certainly not. Even if you were looking through an eyepiece of a telescope, you wouldn't really notice that. So you only really pick up those kinds of things once you have, the instrumentation and the software to actually go through that analysis. And so, sorry, I don't know that distance right off. Any other questions?
What size telescope do you have targeted for the add-on observatory?
Well, actually, the add-on observatory, my goal with that was not to make it a dome, it was to make it a roll-off, because it turned out the way I had set it up is I didn't want to have just one telescope, because I have in lecture classes as many as 60 students, and in the labs I have to limit it to about 16 students. So I wanted to have something that I could bring the group from the lab in and maybe have 4 students working on a telescope or something together. So my goal was to be able to set up 4 individual piers and things in there. So we designed it big enough with the roll-off to be able to do that, which we could never do with the dome.
The roll-off, you get more bang for the buck anyhow.
That's right. So that's the plan. Is the sizes, the telescopes probably won't be part of our capital improvement budget.
Paramounts or something in there, put whatever.
Oh yeah, that'd be great. Yeah. So, but it probably won't be anything that sophisticated. I've got a few telescopes ranging from 8 to 11 inches that have been donated to the college or we've acquired through a grant that are sitting there that we roll out periodically for the students to use. So those would be part of that for sure. And so it'll be kind of a smattering. I've also got some really cheap ones that people have given us that sat in their closet for 10 years, which actually is not a useless thing because it really gives students an understanding of things like aperture and what you can see, and some of them are not automated, so they have to learn how to read coordinates and move them around. And I would like to have that as part of the group of them, so they really understand the advantages and disadvantages. I'd probably have one Alphaz mounted and one equatorial mounted at least, so that they could see the difference there too. So just as many as we could throw in there with different configurations, so they really go, oh, I kind of get it.
Yeah.
And I get why we do it this way and why that's good and why that isn't good. So that would be the goal. Yes?
Prerequisites for entrance into your program, and is your labs, are your labs oversubscribed?
And I wouldn't really call it a program. I mean, well, it's weird how the university defines programs, but I mean, these are courses. I mean, it's within what I guess they call the liberal arts program. It's not really an astronomy program per se. It's just astronomy courses. But I do offer the lecture and the lab. The labs are oversubscribed. In fact, the very first semester I offered the lab, and I can only take 16 students because we have 16 computer workstations in the lab that we use, and they're all working, I also do, in fact, next week we're starting a 3-week, what I call a capstone project in the lab. So they've learned all this stuff all semester. They've done astrometry and photometry and all these different things, learn how to use the software. Next week I walk in with a bunch of handouts, and I give them a set of images. And I break them up into teams. And I say, I'm walking away for a while. And you guys work as a team, and here's your images. And in fact, what the project is Cleopatra, and they have to do the astrometry and photometry. They've never worked with those images before. So they have to do the light curve, they have to figure out the rotation period, they have to measure the coordinates and the velocity of Cleopatra through the sky. And I basically come in very intermittently and say, I'm weaning you now for 3 weeks, and they work as teams, and they all work on subsets of the whole series of data, and then they have to get together and put all their data together as a group to complete the whole thing. And I did that just for the first time last semester, and it was actually very successful. The students liked it because they're all sitting there I mean, I never saw the lab so active. They're all running around talking to each other, and what's going on here, what's going on there, and they teach each other, and at the end, they really figured out some stuff. And then there's a couple little things I throw in there to make them really think about what's going on. When they go to look up the actual data, they can get the rotation curve easy, and that's standard. But when they measure the velocity of the asteroid, they look up what the velocity is on the web from some site, they go, oh my God, why are we so far off? And it turns out that what plays a critical role in that is where the Earth was relative to that, and are we passing it up or doing something else? And they don't really have to do those calculations, but I like them to think about, when we measure things we're on a moving platform, so everything we measure from the Earth we have to take that into account. And it's things that they don't normally think about. So anyway, not to really go off on that total tangent, but that's sort of where we are here. And with the lab, the first semester I ever offered it, I offered one section. And I was kind of worried, like, oh God, I'm not going to get enough students. Filled up right away, and the next semester I was only able to offer one because of scheduling. But this year, for the first time, I've offered two. They both filled up very early, and there's students on a waiting list to get in. And so I think, it's not that they all want to become astronomers or anything necessarily, but usually they have to take labs of some kind, and a lot of them are much more interested in astronomy than, say, dissecting something. It varies, but a lot of them do have an interest, and they learn a lot of stuff in there. So it may eventually end up being where I have to offer 3 labs.
And are there prerequisites? As in
The prerequisites aren't too serious. I usually require at least the completion of intermediate algebra, because they do quite a bit of math in the lab. More than most of them, most of them have done some of the math in a math class, but they've never had to really think about how to use it. And a lot of them are going, wow, some of them are going, oh my God, math. And then others are going, I never realized how to really use this, and they kind of thought it was cool. It's like, I'm actually using it for something. Now I see why I needed to do this. And they do some things with the Pythagorean theorem and other things, and then there's a little bit of trig, but I don't make trig a prerequisite. I tell them something that they need to know in order to do that. So the prerequisites are pretty benign, and it's mainly because we're dealing with freshmen and sophomores mostly, and so I don't want to make a calculus prerequisite or something. And you would just really have a lot of students that wouldn't have the opportunity to take it. So, and the prerequisite also is that they are either concurrently enrolled in the lecture or have completed the lecture course, because the material. They're 2 separate things. It's not one integrated course. They do that a lot in the UH system. So they could take the lecture without the lab, or they could take the lab without the lecture, but they can't do the lab unless they've done the lecture first. So they have a basic understanding of concepts and terminology and things that we actually apply. So we talk about a lot of things in the lecture, and then we come into the lab and they're actually doing the measurements. For example, they're learning how to measure the mass of a planet by observing how things orbit around them. And in the lecture class, we just talk about it. And although I show them kind of how you would do it, but it's not like they're working with images and going, oh, I actually did it. I'm measuring the mass of Jupiter or the rotation of the sun or something of that nature. So it's kind of cool. And typically the students who are doing both do a lot better in the lecture because they have a more conceptual understanding of, like, I really see how all this fits together. So it's kind of cool like that. Yeah.
Have you considered making a video of it yet, your classes and lectures, you make some of the labs?
A long time ago, because they've done TV classes at the college for a long time, I did those in the very beginning. There was like 3 of us that did the first TV classes, and it was in this old funky studio with 1 camera and 1 person there. My problem, as you probably see, is I like to walk around a lot, when I'm talking. And with 1 camera, the guy is trying to follow you around the room, and so in the background, everything is going, and they're going, that doesn't work on TV. And so I had to sit there and kind of, and the main reason I don't do them now is because a lot of the things that I use a lot of animations and simulations and things, don't come across on TV very well. I've tried it, and I've done things, with Molokai and others, and it really, and there's things I can't do that I can do in the classroom. So that's limited that aspect of it.
Well, you're a great lecturer. I must point that out in case you didn't notice. And with a good post-production, I suspect, maybe at your school, the animations can come later. I mean, the people that
There's-
probably are learning how to do that.
There's ways that it could be done. I know there is.
You know, they're expensive if you take them outside, but at your school, you probably can find people that would be a great learning experience.
Yeah, there's ways some of this could be done, and I guess the main unfortunate aspect of it is having the support to be able to really do that with our personnel and our staff, and not that they're not capable. It's just that we're really, minimal in that sense. So it's hard for us to say, let's just dedicate. I'm giving you a whole semester to put together this course.
Maybe a year or two.
Yeah,
Astronomy doesn't move that fast.
I know. So, but there's little things that I'm trying to incorporate in, and maybe eventually. I don't know if it'll ever be a complete package, but it's fun and
The UH system.
yeah, there we go.
One of the things the UH Manoa is getting into is virtual worlds. There's a lot of support and things for that from around colleges throughout the world right now.
Yeah.
So there's a lot of techniques and capabilities that you can bring in easily from a classroom. And I've been involved for about 3 years in putting different businesses together in that for remote teaching and stuff too. And they're looking for a presence, for the IFA to have a presence in what they're doing. So by all means, if there's some way that we can work together and do something, I'd be very happy to.
Yeah, well, I think it'd be great, and it'd be a real interesting thing. And I should mention, since this came up, and I didn't mention this before, this whole idea with students working on remote telescopes. Our students aren't the only one working on those telescopes. So what's happening now is that we're starting to be able to collaborate, have our students collaborate with students on the mainland, in Europe, in other places, and they're starting to see how to work together on different aspects of a project, and then communicate easily these days. And that was a whole other benefit of the thing, where students on Maui can work with students in England or France or Australia or New Mexico. And we're starting to get together with other teachers who are interested in doing the same kinds of things, so that we can develop some projects that our students could work on, either as individuals working with other individuals or small teams. And that's something that wasn't really possible not very long ago. So it's evolving into lots of different things, and that gets them pretty excited too, because it's like they're working with these people who they've never met, but they're all doing the same kind of thing. It's pretty cool.
Twitter with a purpose.
Yeah, there we go.
There's, I think, they're offering, including aquaculture, is a big presence in the virtual world, and they've got students from all over the world that attend the classes, the online classes.
Yeah.
So
yeah, it's really
it's
a
a matter of structure and how you do it, but,
That's right.
but it's possible to incorporate everything, and there's lots of help in that area now.
Yeah, cool. All right, we'll check into that.
So what's planned for your fall? What's your project coming up? Do you have anything on there?
A person that I've worked with in California has been doing a lot of variable star studies for quite some time. And, I mean, there's tons of them. I mean, there's just so much out there. So he's got a group of people that are at Cal State San Luis Obispo who are working on some projects. And he's expressed an interest in having a couple of our students, or one of our students, work with one or two of their students on. So they've got some ideas. I would also, one of my other projects is I'd like to get the students now to move a little deeper into using this new network of telescopes that we have to see what we can actually do with it. So we might want to do some follow-ups on exoplanet transits, for example, and things of that nature, where we can confirm things that, it's not like we're out discovering that stuff, but the fact is it's a discovery for students who are doing it, and when they see that what they're getting is good data, then they feel confident to go on to something that might be different.
So rechecking previous calculations to help lay a groundwork for them?
Yeah, some for example, on asteroids a lot, there's various things that might perturb their orbits and change them a little bit. Or sometimes there'll be ones that get lost. They were observed for a while and no one's seen them for a period of time. And so people will go out and do systematic searches and try to recover them, or to maybe come up with data so they can recalculate the orbits and refine them a little bit. There's lists of things called potentially hazardous asteroids that people always want to get more information on. So there's a lot of things through the Minor Planet Center and others that's just literally wide open, for students to get involved with. And so those are kind of interesting, and I think there's lots of things we can do then where we can do follow-ups. And if I have them work with asteroids that are known and they can come up with accurate astrometry and things, I feel more confident that they can go out and look for other things and submit, if they find something, submit astrometry results and say, okay, I know they're doing good work. I don't have anything definite yet in the fall. I'm trying to just get through this semester at this point, but I think those begin to develop, and I see more collaborative things starting to happen. Yeah. Thank you guys.
Great. Let's thank Professor. Great job. And normally they announce next month's, but nobody briefed me on this. But I think we're having a talk next month. Same bat time. So,
thanks for coming, everybody.
Pretty sophisticated.